Hello students, welcome back. Today in this video we are going to discuss and learn about some important definitions in this chapter. So first one, the greatest common divisor. The greatest common divisor we have got in lower classes as the ACF, that means highest common factor. We can say it as greatest common divisor also. So the definition, when if let a and b be two integers and d is any integer such that d divides a and d divides b. Okay, so a and b are any two integers and d is another integer which divides a and b both, then d is known as the common divisor or factor of a and b. Of course, say like 12 and 36. Okay, we know both 12 and 36 is divisible by this 4. So we can say this 4 is a common divisor or factor of this 12 and 36, but not greatest common divisor. Okay, the definition of greatest common divisor is given here. See, if let a and b be two integers and d be any positive integer, and then d is said to be a common greatest common divisor if d divides a and d divides b. Of course it has to be, but there has to be another important thing for to complete the definition of GCD, and that is for any integer, for some integer c also divides and c a and b, and then c should be less than this, equal to this d. That means other than, so we took for 12 and 36 we took 4 was the common divisor, but remember you have here 12 also which divides both this 12 and 36, and there is no other number which divides this 12 and 36 greater than this 12, but we have another number 4 which is less than this 12. That means the divisor, the common divisor which divides which is the greatest actually, or we can say that means if we take if we have d as the greatest common divisor, that is GCD, then that means there will exist some other integers also which divides c and a which divides a and b such that this c is less than equal to this d. That means c will be less than d. Okay, so this is the definition of GCD. Then we have a theorem. Okay, this you have to remember, for any two integers a and b, at least one of which is non-zero, then there exists another two integers x and y such that GCD of a comma b we can write as ax plus by. We can take any values of x and y, we can write like this. Okay, then we have the definition of relatively prime, that means the prime number. So we know that two integers are said to be, if they are non-zero, they are said to be mutually prime to each other or relatively prime when their ACF is equal to 0. Here we say when their GCD is equal, not ACF 0, sorry, ACF equal to 1. Here we say GCD equal to 1. So they are said to be relatively prime to each other or relatively prime or mutually prime if their GCD equal to 1. So if a and b, for a and b, GCD of a and b equal to 1. Then another theorem, two integers a and b, there exist two integers and it is given that they are relatively prime to each other. They will be relatively prime to each other if there exists any two integers x and y such that ax plus by is equal to 1. So you can say two integers, say for c and d, if you take for c and d, and in order to take this, or in order to get this 2 as prime, if cx plus dy is equal to 1, we can show like this, then we can surely say that c and d are both mutually prime to each other or relatively prime to each other. Some corollaries are very important. This one, GCD of AB equal to D, then if you divide it, GCD of A by D and B by D is equal to 1. We will utilize this one. If A divides B and B divides C and GCD of A and B equal to 1, then AB also divides C. This is one of the important corollaries. Okay, we will be using this one. That means if A divides C and B divides the same number C and A and B are relatively prime, and that means their GCD is 1, then their multiple, see the divisor, their multiple also divides that number C. Then of course we have Euclid's lemma. If A divides B into C and GCD of AB equal to 1, then A also divides C. Understood? A divides BC, the multiple of two numbers where you find the GCD of A and B equal to 1, then A will divide C. Of course, it has to divide. Yes. So we will be using this one. These are important. Okay. Euclidean algorithm we got before this one. Lemma. If A is equal to BQ plus R, then remember GCD of A B is equal to GCD of B R, where R is the remainder. And if A and B are any two positive integers, then GCD of Ka and Kb is equal to K into GCD of A and B, where K greater than 0. That means you can, as if you are taking out that K from this one. Okay. These are important things we have to remember, and we know how to find out the GCD, which is given in the general maths. Then what is LCM? LCM of any two integers A and B is that positive integer m such that A divides m and B divides m, and there will be another integer C where m is always less than equal to C. Itself from the word you can see lowest we know, like 12 and 36, the LCM is 12. That means least common multiple or lowest common multiple, because their common multiple is there 12 and 36. If we will take, what will be the LCM? We know how to find out the LCM. 36 it will be. That means their common multiple is 36, and all those, and this is the least one. That means all the other multiples are less than this 30 are greater than this 36. So that means if m is the LCM, there has to be another integer C which is greater than equal to C. So that means it is the least one actually. Okay. So how you write LCM of A comma B? Then this one we have got the relationship between HCF and LCM of two numbers. We know HCF into LCM of two numbers is equal to product of the two numbers. Same way we will do it here. GCD of AB into LCM of AB is equal to AB, product of the two numbers. Okay, this one you can use. This is important, and using all this we can go for the exercise. This is another way, single arrangement method. This also is instead of doing the Euclid's division algorithm, you can also use this method, where you have to say, here you are asked to find the GCD of 143 and 227. So what you need to do, you have to write the smallest here, the greatest one here, and then you divide. So 143 one time is 143. Then this subtraction you have to again divide this 84 by this 143 by 84. Then what will one time you can give, this is one time, so it is 84, so you get 59. Okay, then this 59 will divide this 84. 59 one side 59, so you have 25 as a remainder. Then this 25 will divide this again 59, so 25, you can see 25 when it is divides 59, you will have 2 times, so 50, you get 9. Then this 9 will divide again 25, so 9 2s are 18, 18 we have another 7. This 7 will again divide the previous number, this 7 will divide this again 9, so one time you will get 7, so on subtracting you will have 2. Then this again, this 2 will again divide the 7, 2 3 times is 6. Okay, last we have the, so whatever the last non-zero remainder is, that will be the HCF. Okay, the last non-zero remainder is known as the HCF. So this is the way you can find out the HCF or GCD of any two numbers using this single arrangement method. That means first you have to divide this one, okay, and then whatever the answer is, okay, here 84 have remainder, you have to divide this again 143, and you have to write this one on either sides. For dividing this one for 143 we wrote 1 here, and when you got the remainder, we have to divide this 143, so one time we can give, so we will get another remainder. Again this remainder, this 59 will divide this 84 one time, again another remainder, again remainder will divide this 59. So likewise, like this we have to continue doing. Okay, then we can head on to the exercise. If it is mentioned to do with the help of single arrangement, you can do it in this process also. Thank you.